the set x belongs to x such that gx greater than fx is measurable. So that means its complement must be measurable because the class of measurable sets is sigma algebra. So what's its complement? Its complement will be gx less or equal to fx, or you can say fx greater or equal to gx is measurable. It's the complement of the above set. Okay, so that's part B. Part B actually, x belongs to x such that fx greater or equal to gx is measurable. And similarly the set x belongs to x, this fx less or equal to gx is also measurable. This set is also measurable. Simply by changing the rules of f and g. So we can replace f by g and g by f here. So it will follow. It's something like this. Okay. Now C part. In C part we need to show that the set x belongs to x such that fx equal to gx. That set is also measurable. So x belongs to x such that fx is equal to gx. And this set, it is the intersection of two sets actually. It's the intersection of these two sets. X belongs to x such that fx greater or equal to gx. Intersection x belongs to x such that fx less or equal to gx. This equality, it is the intersection of these two sets, and both the sets are measurable by part B. So their intersection is also measurable because the class of measurable sets is sigma algebra. It's closer under countable union actually. So it is the intersection of two measurable sets, which is again a measurable set, and this intersection is equal to the equality of x equal to gx. So hence the set x where fx equal to gx is measurable. So that proves the part third of the theorem. Okay, this is the end of the theorem. So let's prove this theorem for a measurable function is or you can say let f comma g from x to r be measurable functions. Be measurable functions. Then the following statements hold. Following statements hold. Then following statements hold. Okay. The first statement is their sum is also measurable. F plus g is measurable, and the second one is that their product is also measurable. Product of two measurable functions. It's the component-wise product. Okay, is measurable. And the third one is their mod is measurable. The positive parts and negative parts are also measurable, and f minus are measurable. So we define these f plus and f minus are measurable. Okay. The fourth one is the maximum of f and g, or you can say supremum of f and g, and the infimum of f and g. The join of f and g and meet of f and g. So join means the least upper bound of the function f and g. And this is the meet. It is the maximum of these two functions. So this is this join and this meet is actually its point wise. So for each point x, you have to find the maximum of fx and gx. That's the value of the join of fg at x. And for each x, you have to find the minimum of fx and gx. That will give the meet of f and g at that point x. So this is also measurable, or measurable function, or measurable. So let's prove this first part. So it's, they are very simple, not too difficult. These two parts, these four parts. So first we see that. First we verify that. First we verify that for any constant c, for any constant c minus g is measurable. G is measurable, but you show that this c minus g is measurable function. Whenever g is measurable, then for any constant c minus g is also measurable. The constant minus g, c minus g of x minus c minus g of x. Okay. So this function, it's or you can say, suppose for constant 2, if g is measurable, 2 minus g is measurable, 3 minus g is measurable. For any constant c minus g is a measurable function. So let's first verify this. Okay, so we have this. What's this? Let's find this c minus g inverse. C minus g inverse. So let's try to find this. Or you can say a to infinity. We show that this set is measurable actually. Whenever we prove this is measurable, this means c minus g is measurable. But what is this actually? It's the set of the points x such that c minus g is greater or equal to a. The definition of inverse. Set of all those points such that the images of those points lie in this interval a to infinity. Okay, such that c minus g of x. Actually, you can see c minus g of x. And that's equal to the x belongs to x such that you can say it's here c minus a c, sorry, it's c minus a greater or equal to g of x. And this you can see it's all those points, a set of all those points in x such that the images lies, such that the images are less or equal to a. That means image lies in the interval minus infinity to that, less or equal to. Okay, less or equal to c minus a, which x belongs to x such that g of x is less or equal to c minus a. G of x less or equal to c minus a. And this one it's actually equal to g inverse of minus infinity to c minus a. This one is measurable because g is a measurable function. So it is an inverse image of this closed set. So this is a closed set, okay? It's the inverse image of that closed set. Images are less or equal to c minus a, less or equal to c minus a. Okay, which is measurable? Which is measurable? Which is measurable? So therefore, the function c minus g is measurable for every constant c belongs to R. For every constant c belongs to R. So that proves this one. Now we show that f plus g is actually measurable. So now let's find this f plus g, its inverse image of that set. Let's try to find this inverse image of this closed set. So if we prove this is measurable, that means f plus g is also measurable. But by definition, what's this? It's equal to all points x belongs to x such that f plus g of x is greater or equal to a, greater or equal to, okay? F plus g of x greater or equal to a, okay? And this is equal to x belongs to x such that it's fx plus gx, because addition is pointwise, fx plus gx greater or equal to a, and that's equal to x belongs to x such that fx greater or equal to a minus gx. Now look at this, both the functions f and g are measurable, and we have already verified that whenever g is measurable, then any constant minus g is also measurable, and here is a is constant, therefore a minus g is measurable. So which means that f is measurable, a minus g is measurable, and the set x where fx greater or equal to g, a minus gx is also measurable by previous theorem. Just we have done it in the previous theorem. Whenever f and g are measurable functions, then the set where fx greater or equal to gx is also measurable. And here the measurable functions are f, measurable functions are here f and a minus g. So it means that fx greater or equal to a minus gx, this set is measurable because the functions are measurable. F and a minus g is measurable. Which is measurable by previous theorem. Which is measurable by previous theorem. Which is measurable by previous theorem. So therefore f plus g is measurable. Therefore f plus g is measurable. Is measurable. That's part 2. F plus g is measurable. So now let's prove third part of the theorem. What's the third part? In third part we need to show that mod of f is measurable, f plus f minus are measurable. First we show that mod of f is measurable. So let's first verify this mod of f is we had to prove the second part now. First, this was the first. In second, we had to show the product of two measurable functions is measurable. So let us find that the square of a measurable. First, we show that square of a measurable function is measurable. So we first show that f square is measurable. F square is measurable. We have, let's find this f square. Okay, we have this f square inverse. Okay, inverse. Let's find this inverse image of this set minus infinity to a. Okay, under f square. We find the inverse image of this closed set under f square. If we show that this set is a measurable subset of x, then this will give f square is a measurable function. And by definition of the inverse image, it's equal to x belongs to x, such that f square of x is it's less or equal to a. Okay, because it's minus infinity to a, so that means less or equal to a. So this is equal to x belongs to x, such that f square of x means fx into fx. Okay, less or equal to, it's the product actually less or equal to a. And what's this set? This set is an empty set if a is negative, because it's a square of real number, or you can say it's f square of x whole square. Okay, f square of x, it's a square of real number. So square of real number is always a non-negative real number. So whenever a is negative, So there is no any real number. There is no any x in x such that fx square is less or equal to a negative number. So at that moment, this will be an empty set if a is a negative number. And whenever a is positive number, so we can apply the square root on both sides. So this will give its minus this square of f of x less or equal to a will give minus root of a less or equal to fx less or equal to root of a. So we can say this is equal to empty set if a is a negative number, and it's equal to what? It's equal to the set x belongs to x such that minus root of a less or equal to f of x less or equal to root of a if a greater or equal to 0. If a is greater or equal to 0. So that's equal to, it's phi if a is negative number, and it's equal to, this is the inverse image of, it's f inverse of what, minus root a to plus root a if a is positive. And what's this set actually? It's f square inverse image of that minus infinity to a. Okay. Now look at these two sets. They are both measurable because phi set is a measurable subset of x, and this is also measurable because f is a measurable function. It is the inverse image of closed interval. In other words, it is the inverse image of closed set. And we know that when f is a measurable function, then inverse image of a closed set is always measurable. So both the sets, in both cases, whether a is negative or whether a is greater or equal to 0, the inverse image of that set under this f square is always a measurable set. This is always a measurable set. So which means that f square is a measurable function, which is a measurable set, which is a measurable set. So this is a so therefore f square is measurable function. F square is measurable function. So square of measurable function is always a measurable function. Whenever f is measurable, then f square is always a measurable function. So now we come to the proof of second part. So this we will use this fact in second part. So in second part we have to show that product of two measurable functions is again a measurable function, and we are going to use this one. The square of a measurable function is always a measurable function. So let's prove the product of two measurable functions is again measurable function. So we have f and g are measurable function, and this product fg, it's equal to 1/2 of f plus g whole square minus f square and minus g square. You can see this, but for this we have to show that whenever f is measurable, minus times f is also measurable. Let's first verify that. So now we show that constant times a measurable function is again always a measurable function. Now we show that CF is measurable. Is measurable. C times f is measurable. So for this, we need to show that this CF inverse of the set. Let's take this set a to infinity. I can also choose minus infinity to a. That will not create any problem. Or I can choose closed interval a to b as well. So let's choose this choice here, a to infinity. It's equal to set x belongs to x such that CF of x is greater or equal to a. And that's equal to, this has now two choices. If c is negative and positive, it's equal to the x belongs to x such that fx greater or equal to a by c if c is positive. So dividing throughout by a positive number, it will remain greater or equal to. And if we divide by a negative number, it's equal to x belongs to x, fx less or equal to a by c if c is a negative number. And if c is 0, then it will be, if c is 0, then it's a zero function, which is a constant function, it's always a measurable function. So we take only two values for c, whether positive or negative, not 0. Because 0 is the trivial case. Actually, we have to show that c times f is measurable. So whenever c is measurable, whenever c is 0, then c times f is a zero function, which is always a measurable function. Okay, so that's why we take these two choices: c positive, c negative, not equal to 0. Now look at this. F is measurable, so this is measurable because it is actually so this is equal to, you can see this is equal to f inverse. It's greater or equal to a by c to infinity. Okay, if c is positive and at the same time it's minus infinity to, it is equal to f inverse of minus infinity to a by c if c is negative. If c is positive, it's equal to f inverse a by c to infinity. If c is negative, it's equal to f inverse minus infinity to a by c. And both these sets are measurable because f is a measurable function. So that means this is measurable. Which is measurable? Which is measurable. So that means constant times of measurable function is always a measurable function. So therefore CF is measurable. Therefore C times F is measurable whenever F is measurable. So if C is negative, that means minus F is measurable whenever F is measurable. Now look at this. This identity F into G, it's equal to 1/2 of F plus G by square minus F square minus G square. So because this is equal to F square plus G square plus twice FG. F square plus G square will go with this minus F square minus G square. It will remain here twice FG. So 1/2 twice FG is equal to FG. So this in part 1 we have shown that whenever F and G are measurable functions, then F plus G is measurable function. So that means this F plus G is measurable function, and we have also seen that the square of a measurable function is again a measurable. Therefore F plus G whole square is a measurable function. This F square is measurable, so minus F square is also measurable. G square is measurable, minus G square is also measurable. So it's actually the sum of measurable functions. So it's like this. It's 1/2 of